What we're going to do here is we're going to solve exponential and logarithmic equations. This is from the worksheet from the same title. The first question here is 3 to the x power equals 5. Now, like we discussed in lecture, how you solve these exponential equations is you can either take the common log, log of base 10, or the natural log of both sides. So we're going to try this out by taking the log, common log, of the left side and taking the common log of the right side. Now notice you have 3 to the x power and 5. So here, what we're going to do now on the left side here is we're going to use properties of logs. And in particular, we're going to use what's called the power rule. It's the power rule property. And the power rule works like this. If you have a base to a power, well then you're free to pull out that power and put it in front of your log. And what you end up with here will be x times log of 3 will equal log of 5. Now the x here is pulled out and we have it right there. So we can now divide both sides here by the number log 3. Log 3 is a number. So we could divide both sides by that log 3. We'll get cancellation. We'll finally get here x equals log 5 over log 3. Now this is a number. We're going to leave this as is in terms of a symbolic form. Here's your answer. This is going to be a number that we can approximate to any place value. We're going to keep it simple in this worksheet. We're just going to give you the symbolic answers. So x here is going to be log 5 divided by log 3. And you're done. I just want to warn you that a common mistake here would be that sometimes people think, and this is incorrect, but sometimes people think that this is the same as 5 divided by 3 for that common log. And that is not the case. Okay, we have no property that allows us to do that. So you're done. You solved for x, and that's that. So we're going to use the same approach in every one of these problems. We're going to use properties of logs, power rule, and we're going to take either the common log or the natural log of both sides. So let's take a look at question number 3. We have 2 to the x is 7. Okay, I'm going to take again the log of the left side, and we're going to set it equal to the log of the right side. 2 to the x power, 7. You got that power there, x. You get to pull that power out. You're going to use the power rule for logs. We now have x times log of 2 equals log of 7. Divide both sides now by the number log 2. You get your cancellation, and now x is going to be log 7 over log 2. Okay, and we're done. That's number 3. Number 5. 4 to the x minus 1 power is 5. Again, we're going to take the log of both sides. Log of the left, so log of the right. 4 to the x minus 1 power and a 5. Now again, we're going to use our power rule. We're going to pull out this power. Okay, that power though is not just an x this time. That power is an x minus 1. So I'm going to have to put that in parentheses. Okay. All right, now there's different things that we can do. Remember, we're going to solve for x, and log 4 is a number. So I'm going to get to divide both sides again by log 4. Log 4 is gone. I get x minus 1 is log 5 divided by log of 4. So we're going to add 1 to both sides. We finally get x equal to the value log 5 over log 4 plus 1. Okay, and this is how we can actually solve for x. I want to remind you, sometimes people like to translate that and to move that 1 to the other side, and if you do, just change its sign, and we can very easily solve that exponential equation. This is number 5. Number 7, we have 5 to the x plus 2 is 3. And like I said earlier, or like we talked about during lecture, we can either take the common log of both sides or the natural log. So I'm going to take the natural log of the left and set it equal to the natural log of the right. And we get 5 x plus 2 here and a 3. So using the power rule for logs, pull out the power. We have here x plus 2. The natural log of 5 is the natural log of 3. So don't forget that the natural log 5 is a number. So if I divide now both sides by this natural log 5, cancellation, and we have x plus 2 is natural log 3 divided by natural log 5. We can translate this too. Move the 2 to the other side, but the price you pay is you change its sign. So I get natural log 3 over natural log 5 minus 2. Here's our answer. Number 9. 3 to the 2x is 5 to the x plus 1. So again, we could use either common log or natural log. My personal favorite is actually to use the natural log, but we don't have to. We could use the common log. And that's just as we discussed in class. So this will be 3 to the 2x power, 5 to the x plus 1 power. Now what you're going to have here is this. We're going to have, for example, we could do this a couple of ways. One way I think we could do it, maybe just straightforward. Let's try this out. Let's pull out the power. Pull out the power. We're going to use the power rule here, but notice you got power rule for both sides. So we're going to pull out here the 2x. We're also going to pull out the x plus 1. And what you end up with is the 2x times natural log 3 will be x plus 1 times the natural log of 5. Now, in this problem here, let's take a real closer look. We have here, let's change this color. Let's see if this works. We got x's here on opposite sides of an equation. And whenever we have this situation, what we're going to need to do is we're going to need to use the distributive property here. Because we want to actually get x's on one side. So on the right side here, we don't do anything on this left, but on the right side, we now get natural log 5 times x plus the natural log of 5. This is by the distributive property. And I guess what we could do here now is, all right, let's try this out. I want you to pay attention to this detail, that x again still is on opposite sides. We want our x's on the same side. So I can translate, move this term to the other side, or simply subtract natural log 5x from both sides. Okay, subtract it. Now on the left side here, you have 2x natural log 3 minus natural log 5 x. We forgot to put the x here. Here's what we have. Oh, no, we got it. Sorry. Minus the natural log 5 x. This is going to be simply equal to natural log 5. So I actually prefer to just think of this as translation, and it's not a big deal. Notice our x is here and our x is here. We have the x on the same side of the equation. Now this is important because what we can do now is factor out that x, and what you're left with is 2 natural log 3 minus natural log of 5 on the left hand side, and that's going to equal the natural log of 5. So what you can do now is this. Remember, x is multiplied to or by 2 natural log 3 minus natural log 5. This is a number. So if I divide both sides by 2 natural log 3 minus natural log 5, I get cancellation here. And we end up simply with our x equals natural log 5 divided by 2 natural log 3 minus natural log of 5. Okay, let's write this a little better. Let's take a look at what we have here. Now, this is perfectly acceptable as an answer. This is fine. And if you turn this in, you did solve for x. I wouldn't mark it wrong. That one's okay. That one's correct. But I want you guys to notice something interesting here. Let's note. Pay attention to, in our note, we're going to use properties of logs. If you consider the denominator in this question now, right down here, we could use properties here to simplify this. What I mean by that is 2 natural log 3 minus natural log 5, we can simply write as a single log by properties of logs. Remember, this here is a power, so I could use power rule and say this is natural log 3 to the second power. There's that 2 power here, and we still have natural log of 5. Now this gives us natural log of 9, because 3 squared is 9, minus natural log of 5. So we can actually write this as a natural log of 9 over 5. And so this is what I'm saying. This can replace your denominator. So in some books, as a final answer, what you can see here is, yes, x will still have the natural log 5 as a numerator, but the denominator will be natural log 9/5. And this is also an acceptable answer. So either of these two are fine. I just want to point out again that the denominator over here, right, used properties of logs to write this as the natural log of 9/5. Anyway, we can do that too, and that might be fun to express our answers. Remember, there's no other property to simplify further from this, and we're done with that question. So that one's number 9. So let's go to 11. And we get 6 to the minus x power is 5. Now, you don't have to use natural log. You could use common log. And let's try common log. So we'll take the common log of both sides. And so this is what this will look like. You'll get 6 to the minus x power. You get the 5 there. So we're taking the log of both sides. Remember this. This power here, by the power rule for logs, can be pulled out, and that's a minus x power. So what you end up with is negative x times log of 6 will be equal to log of 5. Now we're going to actually again solve for that x, and we're going to divide by the number log 6 to both sides. We get our cancellation, and you get negative x equals log 5 divided by log 6. Now that's minus x. So what we can now do is a couple of things, I guess. We can what? Divide both sides by negative 1, because this is really negative 1 times x. And I get my cancellation. And so now we get x going to be simply negative log 5 over log 6. Okay, so here's, looks like it's number 11. 13. 6 to the minus x is 5 to the x minus 1. Again, we could use the common log, or we could use natural log. It doesn't matter. Let's use natural log. I'm going to take the natural log of both sides. I get 6 to the minus x power, 5 to the x minus 1 power. Let's go back here. Use the power rule for logs. Pull out your power. We end up with negative x, natural log 6, x minus 1, natural log 5. Again, we get x on opposite sides. So what we're going to be able to do here is this. We're going to actually multiply, distribute again with that parentheses. We're going to get rid of that parentheses. We're going to multiply both terms by natural log 5. So I have negative x here again. Natural log 6 becomes natural log 5x minus the natural log of 5. My x is on opposite sides. I want them on the same side. So I can do this thing called translation if I want. Let's do this. Let me show you something. I'm going to translate these terms. Remember, translation really means to move, at least in the context that we're talking about here. We're going to move terms. And when we move terms to another side, okay, like I'm going to move this minus x natural log 6 term to the other side. When we move a term, just simply change the sign. Make it opposite. Anything we don't move, like this natural log 5x, we'll keep its sign. Will stay the same. So I'm moving this natural log, minus natural log 5 on the right to the left. It's no longer negative, it's positive. My natural log 5x, I'm not moving, but I'm moving my minus x natural log 6 on the left, and that gives me plus. Let me write it this way, natural log 6 x. So I'm translating terms. I'm moving them. And yet, notice again, we get the x on the same side. And what that means is we can factor out the x. And you have natural log of 5 plus natural log of 6 times that x, that's on the right side. You get to divide both sides now by the number. Natural log 5 plus natural log 6. Natural log 5 plus natural log 6. And we're going to get cancellation here. So on the right hand side we get x. Let's see if we can make some more space. And on the left hand side we get natural log 5 over natural log 5 plus natural log of 6. And we can describe it as x equals, again, we just simply put our x on the left if that makes you feel better. Sometimes people like to see that. Here is our solution. Okay, it's natural log 5 over natural log 5 plus natural log 6. Now, again, I might say to you, by properties of logs, the denominator can be described by properties, right? It's a natural log of 30. Because when you have the sum, we can actually multiply. Meaning, this becomes natural log 5 times 6, or the natural log of 30. So that is going to replace here the denominator, if you so choose. So by properties, we can say x will be natural log 5 divided by natural log 30. So here's another solution you can see, or you can keep the first one. Either is fine. So it's just so nice that we might be able to use these properties. Let's look at number 15 here. Number 15, we have e to the x is 3. Okay, now as we discussed in class, we can take the log of both sides, or we can take the natural log of both sides. This is one of the reasons why I enjoy taking the natural log, meaning I just take the natural log naturally all the time. Because I get in this, if I have to solve this particular exponential equation, let's remember that e is the exponential number. Okay, e is this exponential number. E is approximately 2.718. Okay, it's an exponential number. And so when I take this natural log here of this both sides, and let's go back. Okay, let's take a look at this. Again, we're going to use that power rule. Power rule simply says I can pull out that x. Okay, pull it out. This is what we get. We get x natural log e equals the natural log of 3. Again, e is the exponential number. But let's go back and think again about what the natural log is. Okay, your natural log is log base e, and that's again of e. And you can say log base e, here's the base, e to the first power. And remember, you can look at it either way. That log base e to e to the first power, or of e to the first power, this value is always 1. Or we can say the natural log e is 1. It's the power itself. So if we remember that property we talked about in class, which is essentially this property, right? Log e, e to the any power, is the power. And in this case, the power is 1. And that comes from essentially a function and its inverse, the composition. You could refer to your notes. We discussed this. What I think you want to always remember is this fact. Again, keep that in your notes, that natural log of e is 1. So what that means here for my equation is I get x times 1 is the natural log of 3, or simply x is the value natural log 3. And again, this is why I care about taking, when I actually solve exponential equations, I actually use the natural log, because if I ever get the exponential number, I get this nice property here where the natural log of e is 1. And it's just easier for me to remember, but it doesn't matter. It's up to you. You could use the log of both sides. And this is actually number, I guess, 15. 17 is interesting. 17 is similar. I get 17 here. E to the minus x is 3. Okay, this is number 17. And again, I'm going to say to you that I prefer taking the natural log. So let's take the natural log of both sides again. And on the left, I have e to the minus x. On the right, I have 3. This is my power that I get to pull out. So let's go back. Let's try this here. I'm going to pull this out. Minus x, natural log e, is natural log 3. Once again, the natural log of e is the value 1, and I get negative x is natural log 3. If you like, divide both sides by negative 1. And you get x going to be negative natural log 3. So here's our answer. And I'll just say again, by the way, here's something that you can see, and something that does happen, is that remember that minus natural log 3 is negative 1 times that natural log 3. That negative 1 we can put as a power here by the power rule. Negative 1, it's now a power. And again, from beginning algebra, any number to a negative 1 power is actually 1/3. So you can actually see your answer as x to the natural log of 1/3 as well. Either way you express your answer is fine with me, but I just want to point that out. Maybe if you're going to take a pre-calculus course or a calculus course, you'll see natural log maybe in 1/3, and you need to understand where that comes from. So it's just properties of logs, and this is one of the reasons why you study properties of logs. This is number 17. So we'll call this here a note, or we'll just say by the way. Okay, number 17. Let's look at 19. Number 19, 3e x plus 2 is 12. Now we're going to have to divide both sides here by 3 so that we end up with e to the x plus 2 is 4. Now we get to take the natural log of both sides. E to the x plus 2 over 4. Your power here is x plus 2. I could pull that power out. You're going to have here x plus 2. Natural log e is natural log of 4. Natural log e is 1. So you get x plus 2 is the natural log of 4. We can solve by x by translating the 2, or subtract 2 from both sides. And you're going to end up with x being the natural log of 4 minus my 2. Here's number 19. (21) 4 e to the minus x plus 2 is 18. So we're going to solve for e to the minus x so we could take the natural log. So you can do a couple of things. Again, you can subtract that 2 or translate. You have 4 e to the minus x becomes 16. Divide both sides by the 4. E to the minus x will be 4. So, by the natural log of the left equal to natural log of the right. E to the minus x, 4. Minus x power, pull out your power. Minus x, natural log e, is the natural log of 4. Again, the natural log of e is 1, so we end up with here. Negative x is the natural log of 4. And again, you divide both sides by that negative 1, and we'll get cancellation. And your x is going to be negative natural log 4. As you've seen prior, and I'll change the color again. This also means that x is this means that x is natural log of 1/4. Okay, so here's an alternate way to describe your answer. We already talked about how we got that. And that's number 21. Okay, so now we're going to go to 23. 23. 2 plus 3 e to the minus x is 23. We're going to subtract 2 from both sides. 3 e to the minus x is 21. Divide both sides by 3. We end up getting e to the minus x is 7. So the natural log of the left equals the natural log of the right. E to the minus x, 7. Properties of logs, pull out the minus x. Negative x, natural log of e is the natural log of 7. Natural log of e is 1. And so we end up with negative x being the natural log of 7. Let's divide both sides by negative 1. Cancels. X is negative natural log 7. And again, we can also say that x is natural log of 1/7. Number 25. One minus 5 e to the 2x is negative 24. Translate your 1 or subtract 1 from both sides. What you'll have is negative 5e to the 2x is negative 25. Okay. Divide both sides by the negative 5 here. What you end up with is e to the 2x is positive 5. Now again, you get to take the natural log of both sides. Say the natural log of the left equals the natural log of the right. On the left side we had e to the 2x. We have the 5. Pull out your power by the power rule. You have here 2x natural log e is natural log 5. natural log e is 1. We get 2x is the natural log of 5. Now, here's what we're going to do. You're going to divide both sides by the 2. Your 2's cancel. We have x going to be the natural log of 5 divided by 2. And you're done. Okay, so this here is how we solve number 25. And let's look at number 27. Okay, 27, I have e to this negative 0.02x power is 5. You're now going to take the natural log of the left, the natural log of the right. On the left we have e, negative 0.02x, and I have a 5. Pull out the power rule. Negative 0.02x, natural log e, is natural log 5. Natural log e is 1. Negative 0.02x is natural log 5. So when I solve for x, I'm going to divide both sides by the number negative 0.02. I get cancellation, and now I'll have x equals negative natural log 5 over 0.02. And that's 27. (29) 2e to the x over 2 plus 3 is 7. Translate the 3. You move the 3 to the other side. 2e to the x over 2. Now, remember, you're really subtracting 3. So for some of you guys who want to see this, we get that 4. 7 minus 3. And then we get to divide both sides now by 2. We have our cancellation, and now we get e to the x over 2 is 2. So that when you take the natural log of both sides, we have e x over 2 and 2. Let's move out the power here. And by power rule, we'll get x over 2. Natural log e is natural log of 2. Natural log of e is the value 1. So I get x over 2 is natural log 2. So this time I'm going to multiply both sides by 2 to get my cancellation with a 2. And I'll have x going to be 2 natural log 2. Here's how we could describe our answer. Or we could notice that 2 natural log 2 by the power rule, we can put the constant outside being 2 as a power by the power rule. So natural log of 2 squared is 4. X will be natural log 4. There you go. And this is going to be number 29. Okay. Now we're going to look at the other questions, and the other questions are actually logarithmic questions, or I should say log equations that we're going to solve. Okay. So anyway, let's look at number 31. Let's look at the log equations. So 31, says this. We have the natural log of x equals 1. So we're going to solve for x. We need to know the value of x. And before we actually try to find the value of x, let's go back for a second and let's think about what the natural log is, right? This is really a log base e of x equals 1. That's what the natural log is defined to be. You're going to always use, in this case here, the definition of log. And here's what I mean. That log b of any value, in this case we'll call it a triangle. So log base b of triangle equals square. That this is equivalent to, this is the same as considering this exponential, b to the square equals my triangle. That is really what we're doing here. That is really what we're using. So this means the base here is e. Go back, e. E to the, let's use a different color, first power. First power. E to the first power equals x. So this thing is going to equal whatever color that was, x. In other words, here's what we're really saying. E is the value x, because e to the first power, right, is e. Or we can say x simply is the value e. So you actually solved this exponential equation. You solved it for x. Number 33. And if you just go back for a few seconds here, just simply notice that for this question, all we needed was to use the definition of log. Okay, now if you look at number 33 though, this homework question is log, and it's a common log because I didn't give the base, x minus 9 plus log of x is 1. Now we can't use the definition of log, but what we could use here is a property of log. Now that's a sum, so what that means is I can write this log as a product. I'm using the product rule because the product rule can be written here as that sum. Nevertheless, if we take a look at what's inside now, what's inside our argument for the log, this here says I have really x times x minus 9. That's inside. Now I could leave it like that for now. I also want to point out to you that we just have the word log there, and so by default this base here is 10. So this is log base 10. It just said log, it's a common log. So really what you have here is log base 10 of x times x minus 9 equals 1. Okay, now you have a single log like you had in the prior problem. And what we said earlier was when you have that single log, you're going to use the definition of log. So here's what this means. The base here is 10. So let's do this. 10 to the first power will be x times x minus 9. This is an algebra equation. In fact, it's a quadratic equation now. So when I use the definition, okay, we'll write that there. When we used this definition, we get this purple equation here, which is an algebraic equation, meaning it's x times x minus 9 equals 10. It's a beginning algebra question, really. And so by the distributive property, I get x squared minus 9x is 10. And if I actually subtract 10 from both sides, or I translate this 10 what you notice is you end up with a nice quadratic equation. This is the quadratic that we have to solve. Now you could use any technique to solve this quadratic. In intermediate algebra, again, we actually studied the quadratic formula. So if you liked, you could even use the quadratic formula. If you want, you could maybe complete the square. Okay, that's a method of solution as well. But going back to the beginning algebra, we learned how to solve these quadratics by factoring. And what I find in a lot of intermediate algebra problems, factoring, or I should say, these quadratics are factorable. And so factoring for me is the method of choice. I can factor x squared minus 9x minus 10 very easily. This is 10, this is 1, this is minus, and this is plus. By the product rule, x minus 10 is 0. X plus 1 is 0. Translate the 1. X is negative 1. Translate the 10. X is positive 10. So what I'm looking at here is two solutions. We're looking at, or we're going to say that our solutions here are going to be, let's go back, positive 10 and negative 1. Now I'm going to say, let's be careful here. What I mean by that is this. Notice, if I go plug in these values back into my original equation, if x is negative 1, I got a problem here. We can't define logs of negative numbers. In other words, log of this negative 1 up here, okay, right here, log of negative 10 here, if I actually plug this in, I get negative 10 inside here. Like I get log of negative 1 there. That's what happens when I plug in the value x is negative 1. And logs are not defined for negative numbers. So what that means is we're going to have to throw out the negative 1 as a solution. It's extraneous. Now if I go back then and replace x with 10, well, log of 10 minus 9 on the left over here is log 1. That's defined. And log of 10, that's defined. Log is defined for positive numbers. Because again, the domain for a log, let's recall, and I'll write that down here. Your domain for any log is set of all x such that x is greater than 0. It only is defined for positive numbers. That doesn't mean x can't be negative. It just means that when I go back here and I plug in these values right here and here, I better make sure that I never have log of a negative number. And that means the only solution I have here is the solution that x here is 10. This here is my only solution. Throw this one out. So that's number 33. 35, we get log of x minus log of x plus 3 is 1. And again, by properties of logs, I have log of a difference. I could write this log as a quotient. So this is log of x over x plus 3. And that is 1. Consider the base here. The base here is going to be 10. So this means 10 to the first power is x over x plus 3. Again, we use the definition of log. Let's do the algebra now. The algebra here is going to be x over x plus 3 is 10. We can say 10 over 1, and we can consider this, I guess as a proportion here, equal ratios. And again, we cross multiply if you want to do it that way. And x times 1 just as x, Then I get 10 times x plus 3. And I get to distribute. Let's solve this for x. X is on opposite sides. I get x minus 10x, negative 9x, is 30. If I divide both sides now by negative 9, okay, this cancels. And you get x going to be negative 30 over 9. So I wonder whether this is even possible, or I should say, x could be any value. We just have to be concerned with whether or not our log is defined for this. And notice, if I plug in here the fraction negative 30 over 9 for x, that's enough to tell me that this log value is not defined. I could throw this out. Now, this is the only solution that we got for x. And so if I have to throw out the only solution for this log equation, what this really simply means for us is that the solution set is empty, meaning there's no solution, or we should say no real solution here, but no solution. My log can't be negative. I should say the input can't be negative for a log. And that's what is going to happen to be that solution for number 35. The solution is the empty set, or no real solution. 37. Log base 2 of x minus 3 plus log base 2 of x plus 3 is 4. Okay? Now, let me actually do a real quick instant message so we're not disturbed. Okay, so let's see. This is number 37. So we got a product here. So we're going to write, or I should say, it's a sum, but we're going to write it as a product. So this is log base 2. Let's write this as a product. X minus 3, x plus 3. And that equals 4. Okay. Now, I'm going to say use the definition of log. 2 to the 4 becomes x minus 3 times x plus 3. Now 2 to the 4 is 16. 16 equals x squared minus 9. We get a quadratic equation. Now add your 9 to both sides, or translate. I get 25 is x squared, or x squared is 25. Now here, this is kind of nice because I get to use the square root principle, meaning x is going to be plus or minus square root of 25. And I know that the square root of 25 is the value 5, so x will be here, plus or minus 5. So I'm going to write this as a solution set here, or use solution set notation, that is. And now let's go back here. Now here's what we're saying. Let's go back to the original question, 37. 37 is saying this. Log base 2, x minus 3, plus log base 2 of x plus 3. That's supposed to equal 4. What we're going to be concerned with now is when we plug in a value like 5 here. Okay, let's consider what happens. 5 minus 3 is 2. That's defined. 5 plus 3 is 8. That's defined. So this is actually going to be a solution for us, so we're good with the positive 5 there, okay? Compare that to, however, negative 5. Let's plug in a negative 5 here. Now, what happens here is instead of getting a positive 2 and a positive 8, negative 5 minus 3 is negative 8. Already, I know. I don't even have to check the other number. I mean, if I do, it's going to be a negative 2. I already know that we could never have this happen, that logs are defined only for positive input values. So that negative 8's enough to say, throw out the what? The negative 5 as a solution. So that the only solution, if you really look in back of the book, you'll see the simple 5 there as your solution, and that's the only value that x can be, which is positive 5. It's the only solution to number 37. Okay, so that's every detail. We do have to check, and sometimes we have extraneous solutions, so we have to double check. Number 39, natural log of x plus 5 plus natural log of x plus 1 is a natural log of 12. Well, notice on the left side again we have this sum, so we're going to use or write this as a product. So you get natural log of x plus 5 times x plus 1. And that's a natural log of 12. Now this problem is a bit different because when you use the definition, you're used to this right side actually being, this is a number. Now you might say, well, what do you mean by that? Well, not the natural log. So here's what I want to remind people of. Let's recall we talked about this in class, that let's write this down as a statement again. Let's say if I have the natural log of one thing equals the natural log of something else. So you have the natural logs already on both sides. That's the key. Then we can say that the arguments are the same. That means the inputs are the same. And this fact is a big deal. We talked about why it's a big deal. And it's simply a big deal because the natural log function, okay, this function here, let me go back here. Your natural log function, right? Let's just write it out. The natural log is 1 to 1. This is a 1-to-1 function. So what this means is whatever argument you have here, that's the same as what you have here. That means the following. Let's change this. Okay. Let's go back again and say, change the color. Whatever input you have here is the same as the input you have here. That's what it means. Your natural log function is 1 to 1. Okay. So I can erase this. And here's what we have. We have the product here of x plus 5 times x plus 1 will become 12. And this is a nice quadratic equation. Okay, we can solve quadratic equations from beginning algebra. Okay, or even intermediate algebra. We're going to use FOIL. By FOIL, we get x squared plus 5x plus x plus 5, and that'll equal 12. And you get x squared plus 6x plus 5, and that'll equal 12. Subtract your 12 from both sides. You get x squared plus 6x minus 7 equals 0. Your nice quadratic equation, you could use the quadratic formula. You can actually complete the square if you like, I guess, and I prefer to factor. If it's factorable, we can factor. X and x, 7 and 1, plus and minus. Turns out it was factorable, so we can solve this. We're now using the zero product rule. Translate your 1, you get x is 1. Translate the 7, and we get x is negative 7. Two solutions here. Negative 7, positive 1. So we have to double check. Go back to the original question. The original question here is this. We have natural log base 2 of x minus 3. Oops, sorry. Let's go back. That's not the original. Natural log of x plus 5 plus the natural log of x plus 1 is the natural log of 12. Let's check to see if we have any extraneous solutions. When x is negative 7, we get the natural log of negative 2. Already, we throw this out. We could check the other one just for fun, I guess. But the point being is, this is enough right here. Can never have natural log of a negative. That's enough to throw out the negative 7. Now, plug in 1 for x. And notice what happens here. Again, we get natural log of 1 plus 5, which is 6. Natural log of 1 plus 1, which is 2. This is fine. The natural log of 6 is defined, and the natural log of 2 is defined. So it looks like we're okay. The only solution now here is going to be the value that x is 1. That's your only solution. Number 41. Log base 6 of x plus 7 minus log base 6 of x minus 2 will equal log base 6 of 5. You notice again you have a difference, so we're going to write this as a quotient. Log 6 of x plus 7 over x minus 2 is log base 6 of 5. Again, the log function is 1 to 1. Actually, go back here. Let's recall this is natural log. But what is true, again, is it doesn't matter, again, what the base is. If log base b of one thing equals log base b of another thing, then those things are the same. In other words, if the outputs are the same, the inputs are the same, once again because our log function is 1 to 1. Now that's a log function of any arbitrary base b. So what we're going to say now is this. This means that the fraction x plus 7 over x minus 2 is the same as the value 5. And we could write this as a proportion where we actually use cross multiplication to try to solve this equation for x, and we'll get x plus 7 is 5 times x minus 2. X plus 7 is 5x minus 10. Okay, if you like, translate the 5x, translate the 7. X minus 5x is negative 10 minus 7. So we get negative 4x is negative 17. Divide both sides now by negative 4. See what happens with this x. X becomes positive 17 over what? 4. Okay, now I wonder here, we did solve this algebraically. 17/4. If I plug this in, let's note a few things. 17/4, by the way, what is this number? This is 4 and 1/4, or 4.25 as a decimal, okay? That's what 17, fourths is. So if I plug in 4.25 over here for x, I'm okay, or even better, from the original question, go back here. 4.25 for x, plus 7 there will be 11.25. 4.25 minus 2 here is positive 2.25. These are defined. So we're done. X is the value 4.25. And that one is number 41. 43. Log base 4 of x plus 6 minus log base 4 of x is 2. Again, difference, write as a quotient. Now this is not log on both sides. Here we're going to use the definition of log. This problem is different than the prior two problems because we don't have log over here. Okay? That's what makes it different. We can't use the fact that log's 1 to 1. We're going to use the definition. Now, what that means for us here in this problem is the base 4 to the second power will be x plus 6 over x, or 16 is x plus 6 over x. Put that 16 over 1. If we create a proportion, we'll cross multiply using our algebra. We get 16x is x plus 6, and then translate the x. Or, subtract x from both sides. You end up with 15x is 6. So if we now divide both sides by the 15, right? We'll get x being 6 over 15. Now every fraction has to be reduced. So 6 is written as 2 times 3. 15 is 5 times 3. And my 3's go away. You get 2 over 5. So x is 2/5. You're done. Put that double check. Let's see if 2/5 is acceptable. And notice if 2/5 is here and 2/5 is here, the log of 2/5 is defined, and the log of 6 and 2/5 is defined. So it looks like this value for x being 2/5 is a solution to this log equation. X is 2/5 here. There we go. And we're done.